Welcome to Pure 3. Up to now, you have relied on exact algebra to solve equations. You factorize quadratics and use log laws for exponents. But what happens when you face an equation like x equals cos x? Standard algebra completely fails here. There is no way to isolate x. In this unit, you shift from finding exact answers analytically to finding highly accurate approximations algorithmically. You will learn to command iterative processes that track down roots when algebra gives up. Every algorithm needs a starting point. Before you can home in on a root, you must prove one actually exists in a specific region. The change of sign method does exactly this. If you input two x values into a continuous function and the outputs switch from negative to positive, the curve must have crossed the axis. That crossing is your root. In the exam, you must explicitly state this logic and show your values to secure your accuracy marks. Once you have a rough location, you need a mechanism to improve it. You will learn to rearrange unsolvable equations into an iterative form, x equals g of x. By feeding an initial guess into your calculator, you generate a sequence of numbers that step progressively closer to the true root. Mastering the answer button on your scientific calculator is essential here. It allows you to generate these sequences rapidly and flawlessly, right down to the required decimal places.
However, not all iterative formulas are successful. Some home in beautifully on the root, while others spiral wildly out of control. You will analyze why this happens visually, using staircase and cobweb diagrams. More importantly, you will evaluate the exact mathematical condition for convergence. An iterative sequence only works if the magnitude of the derivative of g of x is strictly less than 1 near the root. If it is greater than 1, your sequence will diverge.
Standard iteration can sometimes be slow. To drastically speed up the process, we upgrade our approach using calculus. The Newton-Raphson method uses the gradient of the curve to slide down tangents directly toward the root. You will take your current guess, subtract the function's value divided by its derivative, and instantly get a highly accurate next step. It is an incredibly efficient algorithm, provided your starting guess isn't dangerously close to a stationary point where the tangent is flat. This unit builds a complete algorithmic toolkit for your exam. You will locate roots by spotting sign changes, build iterative sequences to close in on the exact answer, verify mathematical stability using convergence rules, and accelerate the whole process using the Newton-Raphson method. These are guaranteed marks if you are systematic. Let's get started.